So I'm going to start recording then. So in addition to the training wheels reference, you have some more training wheels ahead of you. You have homework 3 available that I put up over the weekend. That is due, I think, a week from today. Does that sound right? Let me pull up the web page and share the screen so you can see what I see. That's always an important part of the process. So I have, let's see, this is right after spring break. Yep. So, nope, it's in 2 weeks. Your homework is not due for 2 weeks. Nothing is due next week. So I'm trying to give you practice with the univariate approach to time varying predictors because some of you will be using that in your projects, but not a lot of you. A lot of you are going to be needing the material that we're going to cover hopefully next week within the next 2 weeks, the idea of multivariate change. So if you have predictors and outcomes that both potentially have individual differences in change, then your model needs to address the change trajectories for both of them simultaneously in examining how the variables relate to each other. So we're building towards that point. If there's any examples or things that I don't have posted yet that you'd like to see, let me know because I can probably pull at least some early version of it from a workshop that I've given or likewise. So let's see here. We have, yes, so I have the stuff for this week. I haven't posted next week's yet. Your presentation rubric is linked here, and then also your peer review sheets for whichever group you've been assigned to. In the email that I sent you, I told you my logic in trying to make sure that you're not trying to do a peer review at the same time you're trying to prepare your own presentation, but if there's some other conflict that you have with the assignments, please let me know and I'll see what I can do. All right. Any questions about schedule or upcoming work? Any of that stuff? No, we're good to go? Okay, excellent. Then I will shut this down. And we haven't seen each other for like a week and a half. Seems like a while, right? Yes, that was supposed to be a softball question, right? Before I ask, what do you remember from last time, I was going to ask, when was the last time I saw you? It seems like it's been a while. What we were talking about last time, though, was different ways of putting time-varying predictors into a model. So as a way of reviewing, and I'll show you an example of this in just a minute, what's the wrong thing to do? What's the way to screw this up if you have a time-varying predictor and you want to look at its effect on a time-varying outcome? I'm watching the chat, or you can talk to me as usual. What not to do? No one knows what not to do? I find that unlikely. We got one answer so far, conflate between and within person variance and the predictor. Yeah. The thing not to do is to stick your level 1 predictor only in the level 1 model and call it good. Level 1 predictors are almost always level 2 predictors at the same time because people tend to differ in their mean values of any answer that they give repeatedly across occasions. So the trick is trying to figure out how to differentiate the between person level 2 relationship of a time varying predictor from the level 1 within person relationship of the time varying predictor. Including the time varying predictor directly in the model, yeah, without anything else. So that the key here is that the level 2 part of the predictor has to be included as a predictor as well. And there's 3 different ways to do that. We've only talked about one so far, and I'm hoping to get to number 2 and possibly number 3 today as well. So I am on, I think we can pick up here as a good place to start. This is example 4A, and I'm on page 5. I thought it would be good for us to walk through the last model that we talked about as a way of review. Does that sound good? Yeah? Good enough anyway? All right. So we're talking about the story for these data. These are fake data, so they are in the download packet, but they are simulated based on real data. We're predicting a person's glucose level in a log metric the next morning from their responses based on how much negative mood they experienced the day before and also their binary gender. So we're looking at the extent to which between person differences in negative mood or being grumpy as a person And within person fluctuation in negative mood, having a bad day or a good day, translates into differences in glucose. And these are specifically in type 2 diabetics, for which glucose is an indicator of how well managed their diabetes is. So we're looking for stability essentially. So the model that we have here, this is an example of a pure within person fluctuation. Time is not in the story. So it is time varying glucose and it is time varying negative mood, but neither of these variables is going to show systematic change over the course of a 3-week period. So we're just observing these people. We're not trying to fix them or anything like that. So for that reason, there are no variables related to change over time in the model because we didn't need them in the original data. What we do have, though, is an individual intercept like usual, and then beta 1 here is applied to a new version of negative mood. And what do I call this? This idea of mood TI minus mood with a bar over it. What is the name for this type of specification? And feel free to read from the screen.
Person mean centering.
Yes, person mean centering or variable centering more generally. The key idea here is that the mood with a bar over it, that's the person's mean of mood across their rows of data. So that's something I had to compute ahead of time, and you'll get a chance to practice doing in your homework as well. And we are literally subtracting off all of the information about between person mean differences from this variable, hopefully leaving just within person fluctuation that remains as my level 1 predictor. So mood TI is the original time varying mood. The resulting variable when you subtract off the person mean is purely within person level 1 information. That way it can only have a level 1 within person slope. At level 2 then, we stick the person mean of negative mood back in as a predictor. So now we can still look at differences as a function of how grumpy people tend to be, but we've separated the slope for that effect relative to the slope for having a grumpier day than usual. So the reference points for what a unit change is at level 2, it's 1 unit more person mean negative mood. At level 1, it's 1 unit more than your own mean, or what I would say more than usual, more than expected. We also have binary gender here, in which men are the 0, women are the 1, and I've included an interaction between person mean negative mood and gender. That way we can see whether there are gender differences in how average mood relates to average glucose. And I've also included a cross-level interaction of gender with within-person negative mood, so we can see if there's gender differences in the extent to which being grumpier than usual translates into different glucose the next morning. We had previously tested a random slope for the within-person mood effect and found it not to be significant, meaning that people don't need their own version of the relationship at level 1 between negative mood and glucose, but we can still look at a cross-level interaction as long as we've tested the random slope first. And the person mean minus mood, or person mean mood minus 0 here is meant to remind you that if 0 is not a meaningful value in the scale of your person mean, you would want to subtract a constant so that it is. So this distinction of person mean centering versus constant centering or grand mean centering, that is only a level 1 thing. At level 2, there's only centering with a constant because there's no higher level variable to subtract off. You would need a level 3 design in order for that to be there. Okay, does that sound familiar? Yeah? Any questions about the setup?
Yes, I have to listen. Can you hear me?
Yes, I can hear you.
Yeah. So in this case, for example, if we decide to subtract 0 to our person mean, in that case, the intercept now will be centered at person's I mean, right?
If you subtracted a different constant besides 0?
No, in this case, you are subtracting 0. What's the interpretation of the intercept in this case?
So the intercept would be the expected glucose for somebody who is at a literal 0 for person mean negative mood, which this variable had a z-score scaling to it because it was a latent trait. So 0 was already near the grand mean, which is why I left it uncentered, so to speak. I'm just putting this in here as a reminder that you would need to consider that in building your own model.
Okay, so the interpretation of the slope, the 1 unit difference meaning for that slope.
For the
What
person
is
mean
the...
slope?
Yes, exactly. What's interpretation?
For every unit higher person mean negative mood.
Okay. Great, thank you.
And the level 1 slope is for every unit more than your mean. So they differ in what they're relative to, but they're still both in terms of per unit. And you'd have to look at the standard deviation of each of the pieces here to try to figure out like what a unit would be. It's going to be less than 1 because in total, the standard deviation is approximately 1 for the original stacked variable. Okay, other questions? All right, so I have written out in the Stata code and in the R code all of the potential effects that we would be interested in. Most of these are already given directly by the model, but I'm labeling them so that we can contrast how we get them with this person mean centering approach versus a constant centering approach, which is the next half of the handout I'm going to show you. So in general, this approach is going to give us within effects, between effects, and gender differences in those things. We can still get contextual effects as linear combinations, however, and because of the interaction with gender, men are the reference group, so the model is going to directly give us everything for men and how everything differs for women. That means to get what a given slope would be for a woman instead, we have to add the main effect and the interaction term together. So for instance, if I look at the within person slope here, it's given directly by the model in men. That's why the 0 is here for the interaction term. It's given indirectly as a linear combination of the within person slope plus its interaction with gender to get to what it is with women. And if you take these two lines of code and literally subtract women minus men, you get just the interaction term. So the interaction term does directly tell you the gender difference in the within effect. The between effect is the exact same pattern, just swapping out the level 2 predictor instead. And the contextual effect is the one that we haven't talked a lot about yet. That's coming later today. This one is between minus within, is the pattern that we have here for that. I also asked for some predicted values so that I could make some pictures and squared the correlation between the fixed effect predicted outcome and the real ones so that I can get some kind of R square. So most of this I think looks reasonably familiar. The other thing that I wanted to mention, this right here is not strictly necessary. That's my R matrix. So I'm telling it that I want a diagonal R matrix in which the variance for the residuals is the same all the way across days and there's no covariance. I stuck that in here just as a reminder that that's something you would want to consider in your own data, whether you need a diagonal R matrix or whether adjacent days need a lag 1 correlation or something like that. In Elmer, you're stuck with a diagonal R matrix, so there's no code related to that in here. But I've got my formula here that shows I only have a random intercept, and I've got my within person effects, my between person effects, and then the moderation by gender of all of that as well. So if we look through the coefficients then, I think we did this last time. Would it be helpful to go through it again? Or do you feel good with these? Go through it again? Cool. Okay, so my intercept. My intercept is a glucose score of 4.96, give or take, for what kind of person and when?
Average grumpiness when on a usual day for male.
Exactly right. Average grumpy on a usual day when you're at your person mean is when within person negative mood is a 0, given person mean centering, and for a man, because that's my reference for the moderator. So then these two slopes for negative mood, are they marginal or conditional?
Conditional.
Yeah, reviewing vocabulary. Conditional means are they for a specific person or are they for everybody? And in this case, they are specific to men, given the interaction terms. So in men, for every unit grumpier you are than usual, your glucose the next morning. So deliberately focusing on that particular occasion. When your glucose is higher, when your negative mood is higher than usual, your glucose the next morning, it's on the same line of data, is going to be higher by 0.03, and that is significant. Tiny number, but it's in log scales. Likewise, for the person means slope, carries the between effect in this model because that's the only kind of variance that it has, and the level 1 predictor doesn't have any between variance, so it's the total effect at level 2. For every unit grumpier you are on average than other people, so for every unit increase in person mean negative mood, your average glucose goes up by 0.17. So it's not a time-specific effect because this is average tendency in X predicting average tendency in Y. It's a whole shift of the whole line. Gender difference, marginal or conditional?
Conditional.
Yeah. So this is the gender difference among average grumpiness people when they're at their average specifically. That's what it means to be at a zero of these things. So it looks like the pattern is that in women, there's basically no within person effect. It's less positive by about the same amount that it is positive in the first place, so the net is about zero. And the same pattern with respect to moderation by gender for the between. Oops, hang on. Highlighting the wrong stuff here. There we go. The between effect that was positive and significant in men is significantly less positive in women and very near zero as well. So we don't know what these coefficients would be in women. We have to ask for those as linear combinations. The other thing we don't know yet, is there anything in this analysis that tells me whether it would have been okay to smush stuff together across levels? Do I know that based on any of these coefficients?
No, because time isn't at play.
Well, the answer is no, but not because of time not being in here. It's because of what the person mean coefficient represents in this model. So this is not the test of whether the between person effect is more or less than within, it's just the test of it against zero. So I know that in this model, the level 2 effect is person mean negative mood is the between effect. And I know that at level 1, my within person predictor only has within person information, so it has a within person slope. And I can look at these numbers and be like, well, I think 0.03 kind of looks different than 0.17, but I don't have a hypothesis test for that. So that's another linear combination that I can ask, how much bigger is 0.17 than 0.03? The answer should be about 0.14, but I don't know what the standard error for that would be off the top of my head. So yes, our friends' linear combinations rear their heads again. So here's an example of how you can lump slopes together to get an overall test. So for instance, to answer the question, are the effects of negative mood together moderated by gender? I've lumped together the main effect of gender and then the two gender interactions to create a joint F-test for those things. Turns out, yes, they are. And then I have my contest 1Ds and Rs to give me individual slope linear combinations. So it's contest 1D if you're asking for coefficients to be added together or subtracted from each other. It's MD if you're trying to lump them together to get a multiple slope hypothesis test. So in here, the ones that we would need that we don't have are the coefficients for women, for the intercept for the within slope and the between slope, and the contextual effects. So the contextual effects, if we zero in on the coefficients here, the negative one is applying to the within slope, and the positive one is applying to the between. So this is between minus within as the core of what we're asking for. And if we're asking for it for men, then that's all we need. If we're asking for it for women, note that the interaction terms of within and between, the last two spots here, they take on the same pattern. So it's -1 and 1 in the interactions as well, because we're multiplying by 1 for the moderator, and that's why it stays at -1 for this one right here. And then the difference, the gender difference in the contextual effect, is the difference of this line for women minus this line for men, and it's just the difference of the two interactions when all is said and done. So now we have the answer as to whether the effects are significant in women, and as we might expect, they are not. Then we did our squares. What's the difference? He'll do a little review. What's the difference between total R square and pseudo R square? If I were going to write those in a results section, how would I explain that to my reader? Can you still hear me? Yes. Okay, you're just thinking and or typing. Question was, what's the difference between total R square and pseudo R square? How would I talk about those?
Total R squared combines the random effects. Pseudo
Not,
R squared separates them.
yeah, so it combines all of the information in the prediction. It doesn't include random effects though, but it does
So
put
that's
all
the
the piles.
fixed.
Yeah,
Okay.
yeah, it does put all the piles back together in the sense of like how much variance in Y have we accounted for, like as a unit, like how much variance in glucose, period. But we do not put random effects into the predicted outcomes. To me, that is cheating because those are still error terms. So yes, total R square is exactly the same as it would be in a single level regression in that it's the square of the correlation between the fixed effect predicted outcome and the real one. Pseudo R square, then, how does that compare? What makes it different?
That depends on the random component we are interested in. So we can have as many pseudo R squares as piles of variance or sources of variance we have in our model.
Exactly right. Pseudo R square is per pile. So we have, in this model, only two variance components, just a random intercept and a residual, but that means each of those can potentially be reduced with effects at its level. So in your homework, I'm asking for pseudo R square, and in the instructions I tried to clarify, this is what should have happened. So I'm not asking you to estimate more models than what you already have to answer the questions. It's like theoretically, which of these fixed effects should have reduced which variance component. So we have the residual variance at level 1, the random intercept variance at level 2, and I have a comparison relative to the empty model here. The residual variance at level 1, which of my slopes should have been responsible for reducing that? The within person slope or the between person slope? Residual variance at level 1, which of my two slopes should have reduced it?
Level 1 predictors?
Yeah, the level 1. And in this case, if I'm talking about the full model, I also would have the gender by level 1 interaction as reducing the level 1 slope because the within slope doesn't have a random slope to go with it. So any cross-level interactions reduce level 1 variance as well if the level 1 variable that's part of the cross-level interaction does not have a random slope. That means that the other terms must have reduced the intercept, including the main effect of gender, the main effect of person mean negative mood, and the interaction of the two. All three of those would have targeted the level 2 random intercept variance instead. All right. And we made a picture, walked through the picture last time. So in these sorts of pictures, the x-axis that I used here is within person negative mood, where 0 would mean we're at your usual level, whatever that happens to be. Differences between people and what is usual are displayed by differences with these different lines here. So I have blue lines for men, red lines for women, solid lines for grumpy people, and dashed lines for happy people. So the gender differences are by color, the person mean negative mood differences are by line type, and the fact that the two blue lines are much farther apart than the two red lines are is the gender by person mean negative mood interaction. The very small slope of the x-axis here, that's the within person slope, and it's a little bit stronger in the blue lines for men than in the red lines for women. I've also cheated the y-axis considerably so that we could actually see these patterns. So this is a do as I say, not as I do situation here. Don't cheat your y-axis quite so bad. But it's a weird log metric that no one knows what these numbers mean anyway, so. All right. Any questions on that so far? And I remember I think we had gotten to this point and I surprised myself by the fact that I had M+ code in here. As if someone else put this in here. It turns out I did it. So a lot of you are heading into M+ because you're going to be in multivariate territory, trying to predict multiple outcomes at the same time or fit growth curves for multiple outcomes at the same time. So I wanted to continue giving you some exposure to what it would look like in MSEM software. So this model then is not technically a multivariate, multi-level structural equation model. This is a univariate model. I'm just using the fancy software to estimate it. So I've made all of the variables ahead of time that I need to fit in this analysis, with the exception of the level 2 interaction. So I made within person negative mood, I made person mean negative mood centered at 0. The only one that I have to make for this analysis is right here, because in M+, you have to make your interaction terms ahead of time for single level interactions. So if both of your predictors are at level 2 and you want an interaction, you have to make that as a new variable. The same is true at level 1 if you have two predictors at level 1 and you want their interaction. So I tell it how my data are clustered, which is my person ID. I tell it which variables are to be treated purely at level 1 and which ones are purely at level 2. So within person negative mood is a variable that I created only having level 1 variance, and person mean negative mood only has level 2. Question, when you say you made those variables, you made them in a different software before putting them in M+. That is correct. So I probably outported, exported, outputted. I'm going to go with outported. That's a new word. I outported data from SAS is most likely, but you can make a CSV file for M+ out of any package. M+ does have a capacity to do some data manipulation, but it's problematic from a perspective of order of operations sometimes, where I can't get it to do things in the order that I need them. And so it's usually easier just to prepare your data in whatever software package you're most fluent in and then bring it over here. The exception being this one interaction term, since I wouldn't have needed that in SAS or Stata or whatnot. So I can say that within person negative mood goes on the within line because I've set it up that way. Like I've withined it myself, if I can make that a verb. I'm using maximum likelihood instead of residual maximum likelihood because that's my only choice. I could also add the R after it to control for potential deviation of multivariate normality. In the within model here then, I'm writing out everything that is going to be estimated. So some of this happens by default, but I prefer to be explicit in my code. So I'm writing out my reference to the outcome variable because that is referring to its level 1 residual variance. I am using the placeholder notation to define the slope of within person negative mood. And the reason that I have to do it this way in this model is because I'm including a cross-level interaction with gender. So if you are going to have anything beyond just a single fixed level 1 slope, you have to do it with this placeholder notation. So within person negative mood is essentially beta 1. Quit it, word. It's like trying to help me spell this better. No, I spelled it the way I want. And my choices should not be mood or pod. Thank you very much. Can I do... There. That works. So within person negative mood is beta 1. That is going to become a latent variable from the perspective of this way of estimating things. And it is the slope of glucose as y on x as within person negative mood. So it's written somewhat backwards, but think of on as your equal sign in an equation and you should be okay. Then at level 2, I have the mean of my glucose. That's the fixed intercept for my outcome. I have the variance of glucose. That's my random intercept variance for my outcome. The name of my placeholder variable in brackets here, that's my fixed within person mood slope. I am shutting off the variance of it, meaning that I don't want a random slope variance in this analysis. I only want it to be fixed. And I am putting in the cross-level interaction then as the slope on the predictor. So it looks exactly like the level 2 equation does, in that beta 1 is predicted by gender as its only cross-level interaction. Then we have the level 2 effects of person mean negative mood, gender as the main effect, and then the interaction variable that I had to define here. So in this analysis right now, there's no advantage of doing it this way over Elmer, SAS, what have you. This is just a straight up univariate multi-level model. There could be a disadvantage of doing it this way from the perspective of not using REML estimation and not using denominator degrees of freedom, which matters more if you have smaller samples. One advantage that I could have that I didn't put in here so that I could keep it congruent is missing data. If my predictors had missing data, I could bring them into the likelihood by estimating an empty model at either level. So I could do it for the within person negative mood at level 1, between person negative mood at level 2, estimate an empty model for that predictor, turning it into an outcome for which missing data are allowed. So that would be one reason to move to this framework, even if it's still, you're thinking of it as a univariate analysis, is to turn it into multivariate for the sake of including rows with missing observations. Model constraint, have we done this in this class before? I don't think so. So model constraint with new is the analog to how you get linear combinations of estimated model parameters. But unlike what you can do in SAS or Elmer or Stata, you can also get linear combinations of variance components. You can get any combination or nonlinear. So for instance, you could ask it to compute an intraclass correlation and get a standard error for it and a confidence interval. When I've had to do genetic analyses where I'm looking at like differences between, say, monozygotic and dizygotic twins and their variance components, you can ask for those types of contrasts and variances as well. So you can do a lot more than you can in the GLHT type of estimate Lincom statement world. So for continuity with the previous model, I wrote out everything that I was trying to estimate. So the new command here, you first have to name the linear combination that you're trying to create, and then you describe how it's created. So I named the intercept for men, and it's formed with only the fixed intercept. For instance, the intercept for women is the fixed intercept plus the main effective sex. And these names, by the way, are up here in parentheses next to the parameter. So in the parentheses, if it's only one name and it's only applying to one thing, it's just a name. If you use the same word in multiple places, it's not only a name, but also an equality constraint. So in order to do math on the model parameters, you have to give them a name. Then you can refer to that name in the equations down here. So for instance, the between person mood effect in women, I've named as BP1, and it's the main effect of person mean negative mood as labeled above, plus the interaction term. And the contextual effects are down here. And you can only have 8 characters, and so I have to get creative with my labeling conventions. Okay, I know that was a little bit quick. Any questions on the M+ code to fit this model? No? Reasonably straightforward? It's okay so far. We end up with my HO value. There's not an H1 value in the MSEM land in a lot of cases. It's never going to be there if you have a random slope. So the 2-level random structure, you only get a few pieces of fit statistics. Let's see here. At the within level, this one is my level 1 residual variance. At the between level, everything else shows up. So this is my cross-level interaction. It lists first. Then we get the level 2 effects on beta 0. The intercept, what is that thing right here? Let me zoom in so you can see it. The intercept of glucose, what is that?
That's the fixed intercept, right?
It is. Now, what is the intercept of within person negative mood?
The fixed slope?
Yes, it is a slope, even though it's under a heading called intercept. So remember that when we're talking about the transition of fixed and random effects into latent variables, the mean of the latent variable is the fixed effect. The variance around that mean is the random effect variance. It's called intercept instead of mean if it's being predicted. So this is the within person mood slope specifically for men. So it's like the intercept of the level 2 equation for beta 1. So this can be confusing, which is why I'm reviewing it here. Likewise, what is the residual variance of glucose in the between model? What would I call that?
Is that the random slope variance
Close. It's for
or random
glucose.
intercept variance?
Yes, I would call that random intercept variance left over. So you know that it's random intercept because we're at the between level. We know that it's the idea of left over because that's what residual variance means in the output. It means predicted things. So this is random intercept variance left over. And this one, what is that referring to? Because it looks like it's like the residual variance for mood, but that's not right. It's a slope. Yes. This is where the random slope leftover variance would be if I had it in the model. I don't have one, but it's left over because this fixed effect has a cross-level interaction with gender, so leftover slope variance would be called within person mood residual variance. Where this gets really tricky is if I were to turn mood into an outcome and use latent centering, which is the next type of example that we have, example 4b. And then last but not least, here's all the additional parameters that I created. So we have the intercepts, the within person slopes, the between person slopes, and the contextual slopes right here. And the line means that section is done. All right. Questions or things that you want to hear again or differently?
So I wanted to ask, just to clarify, the within person differences you were centering on, is this the individual person means? And then the
Mhm.
between person is we're centering on a constant of some sort.
Yes.
Okay.
Yes. At level 2, it can only be a constant of some sort. At level 1, you have a choice whether you want to subtract the person's mean or subtract a constant of some sort. What we've done so far is subtract a person's mean. Now I want to show you the other side. And do you remember which of these I greatly prefer?
PMC, right?
Yeah, person mean centering, because you do the work ahead of time and then you can't screw it up. I'm going to show you the other way too, so that you will know what to do with it if you need it, but also because it's more common and because that's what you end up being stuck with in structural equation modeling or multi-level structural equation modeling in certain types of models. So I want you to be able to figure out what to do with contextual effects when you're stuck with them and how to get back to between. So let me transition back to slides for a minute here. And we haven't talked about constant centering yet at all in this class, have we? Like the difference in level 1, we haven't done this part yet, have we? I'm getting interference because I literally just gave this same set of slides with different subscripts in my APA workshop. And within person snuck in there in a couple places too, despite the best of my ability. It turns out that in PowerPoint, find and replace does not work inside equations. So
I think the last slide was 19, listen.
19, okay, good. Then that jives with my memory, because we did a little example in here, then we did the big example, and now we're ready to start talking about constant centering. So we'll pick up with slide 20 then. So summarizing what we get out of person mean centering, what we get directly is the within person slope and the between person slope. So we get those directly because we set up the variables to only include level specific information. At level 1, the only kind of information that it has is relative to usual. Therefore, its effect on an outcome can only be the within relative to usual, which accounts for residual variance. And notably, this is the case regardless of whether we put the person mean in at level 2. The within slope stays the within slope, the end. Come back. At the level 2 part then, the effect of the person mean carries the between slope. People who tend to be higher on X, do they tend to be higher on Y? And that is the case whether or not the within slope is with it. So each of them stays in their own lane because they each have variance only at their level, they're uncorrelated, and that is the only possible interpretation. What they don't tell us is this thing called the contextual slope. And there are two ways to think of it. The most straightforward way is as the direct test of whether smushing is okay. It tells you how different the between slope is from the within slope. The other way to interpret it is as the incremental contribution of the person's mean after controlling for their value on the time varying predictor at that occasion. So after you control for like your absolute amount of grumpiness on a day, does it matter how grumpy you tended to be on all the other days? Is there a contextual effect of you as a general tendency above and beyond what you had today? Do the rest of your days matter? Is kind of the way to think about it. And we have two choices if we want contextual effects. One is to ask for them using person mean centering, which is what I've just shown you. And the other is to change how we put in our level 1 predictor. Rather than centering at a variable, we center it at a constant of some sort. And yes, I'm going to say constant of some sort. I'm going to steal that, Nathan. I like it, because it honestly doesn't matter what number it is. You can pick 5, you can pick the grand mean, you can leave it uncentered. Which constant only changes the interpretation of the fixed intercept and of the slopes for any interacting predictors. It does not change the information the variable contains, and that's the key. If you center at a constant, your level 1 predictor still contains person mean variation in it and within person variation in it at the same time. Why you get different results then across these two centering strategies goes back to what you learned about unique effects versus bivariate effects in multiple regression. So if I have a single level regression model here with two predictors, if these predictors are uncorrelated, then beta 1 and beta 2 carry the full bivariate relationship between x and y. If x1 and x2 are correlated, then the betas carry the unique or partial relationship, the part of x1 that has to do with y independent of its overlap with x2 and vice versa. So the key idea here is that you have to know whether these predictors are correlated to know how their effects would change when they're put together in the same model versus if you only have one or the other. And the exact same thing is going to happen here in the context of how we decide what to do with the level 1 model. So let's say that I have two people, each with two occasions. I have somebody who has a 2 and a 4 on different days and someone who has a 6 and an 8 on different days. So the average of 2 and a 4 for the first person here would be 3. The average would be 7 for the second person. If I centered, toward, let's center at 5 so that we're talking about kind of the average of these two people, then the person mean variable would look like this, and this is what goes into the model either way. So the distinction of whether you use person mean centering or constant centering is at level 1 only, not level 2. Level 2 is always the person mean, subtracting a constant so that 0 means something. What we had done before is this column right here, person mean centering, where I'm creating what I called within person x by stripping off the person's mean. So the first person is 1 below their average and then 1 above their average, and so is the second person. So this column right here only contains relative information, only level 1 fluctuation around your mean. The mean is over here at level 2. In contrast, the rightmost column here, which I've labeled as grand mean centering, if I subtract the same grand mean of 5, this still contains relative information, like this day is lower than this day, but it also contains absolute information about the fact that this person tends to be lower on average than the second person. So it's both. So the consequence is that the person mean variable is going to take on a different interpretation when it's paired with either of these columns. So here's what's going to happen. If I put in, I'm going to call this time varying x. So it's the original time varying x minus a constant. And then person mean x is the exact same variable that we had before, but it's in a different color because it's going to mean something different. So if I put on my regression hat here and think in terms of unique effects, time varying x has both level 1 within and level 2 between information. Person mean x only has level 2 between. So when I put these two in the same model and they have to compete against each other, what does time varying x have that is unique over person mean x? What does time varying x have that makes it unique?
Does it have both random and fixed effects?
Well, just in terms of the information that the variable contains is what I'm focusing on. The effect that the information is going to have is the next link in the chain. So in terms of its information, what does time varying x have above and beyond person mean x? We got one vote for within variation. Anyone else want to vote?
Between person mean centering, person mean centering is within person variation, right?
If you do person mean centering, then the level 1 predictor only has within person information. This predictor still has both, but after you control for level 2 between, what it contributes uniquely is just level 1 within. So the end result is that even though it's multiplying a different variable, the fixed slope at level 1 means the same thing. It is the purely within slope because of statistical parceling. Controlling for. There's an easier way to say it. So it's a backwards engineering to get to the same spot. Even though the original variable has 2 levels of information in it, it's only the within that carries the slope. And so you'd look at this variable, then person mean x, it only has level 2 variation. You might say to yourself, well, then it's the between effect, duh. No, because level 2 variation is still at level 1. So it also is a unique effect. It becomes the contextual effect. So person mean x carries the incremental contribution of the person mean above and beyond the actual value at each occasion. If I'm grumpy today, that changes my glucose. Okay, cool. Does it change it further if I tend to be grumpy on all the other days? Like, to what extent is a difference extrapolable from the rest of my information beyond just what it would be from trying to predict my daily score? That's the idea. So what makes this confusing, to me at least, is that at level 2, it is literally the same variable either way. It is person mean centered such that a constant means something. But that same variable takes on 2 different interpretations based on what it's paired with. At level 1, it is a different variable either way because we subtract off the person mean or we subtract off only a constant, and yet the slope it carries ends up being the same. It's very confusing. Here's a picture that I think maybe will help. Hopefully not make it worse. I'm not sure that's possible. So on the y side here, we have my intercept variance at level 2 and my residual variance at level 1, and the model has figured out how much should be in each pile as a latent variable. So E is a latent variable from the perspective of estimation, and so is U0. On the predictor side, we have taken our original level 1 predictor here, centered it such that there's a constant, which means it still has the green level 2 part and the purple level 1 part. So that means the slope from it is still predicting the intercept. In order to make sure that the intercept has the right total slope, though, the person mean swoops in here to fill in the gap. So the sum of the blue line and the purple line get you to what the green between line should be. So between is within plus contextual. So the end result is that this model is equivalent to what we had at person mean centering. It just goes about it in a roundabout kind of way. It's equivalent so long as you include the person mean analog for every level 1 term that you put in. Not just main effects, but interactions as well. And that's where it can be easy to screw this up. Let's see, there's a picture. Okay, how we doing?
This makes me like MLM software a lot more, or like the or fixing things at 0 instead of. Unless I'm thinking of something else.
Can you say the first part of that again?
Well, just is this something that we would avoid if we did this in like M plus?
Not necessarily.
Not necessarily.
Not necessarily. No, this is the thing. When I first started learning how to do the between within syntax in M+, as I tend to do, I gave it data where I know what the right answer is. So I can't emphasize this enough. Do not try to use a new package without knowing what you're going to get back, because you won't know if you're interpreting it correctly. And so I fed it in data that I made up the data. I know what the right answer should have been, and I wasn't getting them. It was way off, way off. And then I started playing with it, changing this, changing that, watching the numbers change as I played with it, trying to like deduce what must be happening. And then I finally figured out that what it was giving me was contextual effects instead of between. And that was where I was so mad I had to write a paper about it. So even if you want to have between, you may not necessarily get it because of the way that it's parameterized. And that becomes trickier the more complicated your model is. So you may be in situations where you're stuck with contextual versus between. So I know for those of you who are interested in using like Stan or some other kind of like Bayesian where you write out everything yourself, the difference would be whether you are phrasing your model such that like E is a predictor, like the part of the variable that's just level 1, or the original variable with all the parts put together again. You have control over that if you can write the model and estimate it yourself. Otherwise, you're stuck with what happens, in the black box of M+ or other similar packages. I can show you lots of examples and I can give you some guidelines as to how you can figure out what's going on, though. That's the best that I can do. Here's the picture that I think I showed this earlier because we had questions about the contextual effect, and I added in a new slide at the end of this slide deck that gives you another version of this. But the idea here is that the contextual effect is the vertical distance along this black line. So in these pictures, I have, for instance, time-varying stress as a hypothetical predictor and time-varying severity as an outcome. I have different lines for different levels of person mean stress. And this picture shows a positive effect of stress predicting disease severity, where with the within person effect is the slope of these individual lines, and they're all parallel because this is not an interaction model. The between person slope is the slope of the yellow line through the person means, and the contextual slope is, it sounds weird, but like the slope of the straight line. I don't know how to say that otherwise. It's a vertical distance. So if once I control for the fact that I'm at a 5, like 5 is relatively high for the red person, it's average for the green person, and it's relatively low for the blue person. But if I condition on 5, what is the incremental difference as a function of the person mean? That's your contextual effect. The yellow line is not controlling for an absolute amount of anything. The yellow line is at a within person 0, where 0 means you're at your average, but the averages can still differ. So maybe another way to say it, the between slope does not control for level 1, the contextual slope does. That's the difference. Let's not do algebra. Let me get to the end and show you the slide that I stuck in here. So this is from the paper that I wrote when I was mad about this. And let's see here. You have it on your reading list. And so the first picture here would be a demonstration of when there's a minimal contextual effect. So I have my original level 1 predictor as my x-axis and my predicted outcome as my y-axis, and I have different lines for different level 2 means. And in this case, once I condition on like the original value of level 1, there's not much difference between the lines. They all kind of converge onto the same trajectory. So do you remember when we talked about age and cohort and the idea of like all the different little lines, getting onto the same thing? Like that's this. If you don't have contextual effects, then you don't need to know what a person's average is. Knowing what they have at a given day is enough to draw a line through their data. So the slope is pretty much the same between persons as it is within persons. The contextual effect is very minimal. In comparison, this picture down here shows a between effect that's 0. So the slope of the line through the means here is flat. The within effect is 1, so it's a positive relationship, and the contextual effect is -1. So the question then is, how do you interpret the difference of between versus contextual? Does the level 2 mean matter? Well, it matters, but not it matters incrementally, but not at all. So the example that I gave in the text to go with this is actually for cluster data, in which contextual effects tend to be more useful. So if, let's say, I have SES as a very common example of when you would see a contextual effect, right? If I'm a kid and I'm richer than other kids, then my achievement may be higher than other kids. Yay for me. But at the same absolute level, if I'm a student who is richer than everyone else, I actually may end up doing worse than, or excuse me, if I'm, here it is, let me go this way. The level 2 mean is 1. If I'm from a school that has higher SES students and I'm on the low end of that, I do worse, even though my absolute SES is the same, than a student who is on the high end of a low school. So it's the interpretation that matters. Like, you need to know whether you have a between or contextual, because it's not that schools who have higher X have higher Y. It's that after controlling for the child's X, schools have lower Y after that. So the two different kinds of level 2 effects that you get out of these situations. That's the thing. In longitudinal data, I don't know that contextual is useful. I don't. I would always try to get between if I can. Okay, let me get out of that. So this is a new slide that I stuck in after I had questions about that. Yeah. Okay, do you want to see the example? Did that help? We pick example over algebra, right? Any day of the week. All right, let me go back to the example. So I'm picking up on page 8 out of 16. This is example 4a again. So I'm starting over with my model building process now, using constant centering at level 1 rather than person mean centering, so I can show you what happens. So the first model that I have here is an example of what not to do. So I put in time varying negative mood. I don't need to center it because 0 is already the mean of this variable, and I put it in all by itself without any representation for it at level 2. This is a smushed effect. So I put in my single fixed slope here in my Stata code, my single fixed slope here in my Elmer code, and here's what I get back. So my fixed effects, this is the expected glucose for somebody with time varying negative mood of 0. So I can't say it's for an average person on an average day. It's just 0, whatever that means. With my time varying slope right here of the level 1 predictor is 0.012, which was actually pretty close to what it was before the level 1 predictor. In my pseudo R-square, though, what I see is that the residual variance was accounted for a very small amount, just like it was, but so was the random intercept. So this is your test of whether you know that smushing has occurred. If a level 1 predictor reduces level 2 intercept, can't happen. Only if the level 2 part of the level 1 predictor has reduced the intercept. That is what's happened. The embedded level 2 variance in time varying negative mood is responsible for the pseudo R-square for the random intercept. So let me go back and get the coefficient to compare with. I thought I had it in here, but maybe I didn't. Well, it's showing up here in just a minute. Okay, once I fix it, the within effect is 0.011. In the smushed model, it is 0.012. Now you might look at that and be like, okay, so you're telling me that I need to desperately worry about a slope being different in the third decimal place? Really? Because that doesn't seem very on brand for somebody like me who doesn't try to sweat the small stuff. But here's the thing. This is indeed very close to the within slope because there are 20 days of information for each of my 200 people. So the smushed slope is heavily weighted towards the level 1 slope because that is estimated way more precisely. That has a lot more information going into it. What does this model say the between slope is supposed to be? You don't see person mean negative mood in here, right? So what is this model saying the between slope is?
0?
Nope. Not 0. Good guess, though. That's what you would think. The definition of smushed effects. It's when you are forcing the within and between slopes to be the same number. So this model says the between slope is also 0.012. That's the problem. The between slope is, if memory serves, something like 0.08 or 9. It's 8 times the size of this. So the problem with smushing is rarely in the level 1 model. The smush slope is going to be pretty close to what the within slope should have been. The problem is in the level 2 model. You're not putting in the right between slope in this case. That means that your intercept variance is not going to be the right amount. It could actually go up instead of down if the between slope were in the opposite direction. Like if you put in literally the wrong slope, like in the wrong direction, it could make the model worse instead of better. And all of the things that you would worry about at level 2 are going to have bias to them because you're not adequately controlling for the effect of person mean negative mood. So the problem is in the level 2 model, not the level 1 model in most cases. So we fix it. We put in person mean negative mood, give it its own effect, and that is going to fill in the gap from what the previous model said the between slope should be and what it actually wants to be. We're going to pry them apart, and the contextual slope is the difference after we've pried them apart. So then what we have, after we put in time varying negative mood and person mean negative mood, is these two numbers right here. So the slope of time varying negative mood after controlling for person mean negative mood, now that's within. It's the same 0.011 that we had before. After controlling for the absolute amount of negative mood on a given day, the slope associated with person mean negative mood is not between but contextual. It is the difference. It is how much more positive the between slope is than within. The fact that this 0.06 is significant means that the between slope is bigger than the within slope, more positive, and that we can't smush them together. We can get to what the between slope actually would be by adding within and contextual. So putting them together gives us, about 0.07 or so. So to repeat, trying to put this all back together again. When you put in a time varying predictor without its level 2 counterpart, the result that you get, the smush slope, assumes without testing that the within and between slopes are the same number. That joint shared number is going to be pretty close to within because that's where all the information is. So omitting the person mean is akin to saying that this 0.06 for the difference of how within and between differ from each other is 0. But there's no contextual effect. So what this means in this context, in this story, I should say, not to use the same word, is that even after I control for how absolutely grumpy you are on a given day, there is an extra contribution from your grumpiness on all the other days on today's score too. The context of you matters beyond just today. People who have higher negative moods on average have higher glucose on average beyond just the impact of negative mood today on today's glucose. And if I look at the changes in the variance components, I picked up an additional 1% of the variance in the intercept that is allowed after I allowed the full between slope to take its value of 0.07 that it wanted to be, rather than making it be like 0.01. All right, 141. How are we doing, folks? Are we hanging in there? Ish? Can I show you a table? No more algebra for right now. Let's go to the table. Here's my slide 38. Here's my summary of why I like the person mean centering better. So the first two rows of this table are describing what happens if you use person mean centering, or more generally, in any kind of sampling design, it would be variable centering, where you're removing the level 2 part. So the level 1 predictor only has within information, the level 2 predictor only has between. So regardless of whether the other one is in the model, it stays the same. Whatever you leave out is assumed to have a slope of 0. In contrast, if I do grand mean centering or constant centering, doesn't matter which constant, if I leave it uncentered, if I forget the level 2 part, the level 1 predictor has a smushed effect. If I forget the level 1 part, the level 2 predictor has a between effect, and when I put them together, they both change. This is why I don't like the bottom one, and I try not to do it because it's easy to screw up. You have to be very careful to make sure that you've got the level 2 part associated with everything, not just for main effects, but for interaction terms, and that's what all the algebra is about. But that algebra is going to wait till next time. Fair? Yeah. The algebra, by the way, is because of two reasons. People who say that group mean centering or person mean centering is weird and you shouldn't do it, and people who smush interaction terms without realizing that they've done it. So both of those are trying to convey the consequences of those misunderstandings. All right, 143, that means it's time to wrap up for today. So questions, things you want to hear again. No, fair enough. Then have fun working on homework 3. It is only person mean centering, by the way. You don't have to do it both ways. Give you practice on the preferred way to do it. And let me know as you're working through your project stuff if you have any questions and need help. I have office hours tomorrow as usual, and then on Thursday we'll be back on Zoom. We're getting kicked out of our classroom for comprehensive exams. Okay? All right, then thanks for being here, folks. See you on the other side.